Now there is a word of caution in using the second derivative test, and I have three functions here that I'll use to indicate what that caution is. So let's try to classify the relative extremum for this test. Start out using the second derivative. So remember, we first of all have to find critical points. Take the first derivative, which in this case would be 4x to the third. In the case of f of x is equal to x to the fourth. All right, and so if I set that equal to 0, it'll never be undefined. I get x equals 0. It's not too hard to see. Okay, now if I take the second derivative, to use the second derivative test, I'll get 12x squared, and if I evaluate that second derivative at 0, I'll get 12 times 0 squared, which is equal to 0. It's not positive, it's not negative. Okay, but if you think about what x to the fourth looks like, I have the graph of x to the fourth looks something like this. All right, it looks sort of like x squared, except it's flatter at the what we would call the vertex. This doesn't really have a vertex, I don't think, but it looks like that. So notice that at 0 we have a relative min. So here the first derivative was 0. We were at a stationary point or critical point, okay? And the second derivative of 0, we had a relative min. If I look at g of x, and do the same thing, all right, look first for critical points, I'll have negative 4x to the third, set that equal to 0, and I'll get 0, x equals 0. Then test it with the second derivative. I use the second derivative. Taking the derivative of g prime, I'll get negative 12x squared. If I evaluate this at 0, I'll get negative 12 times 0 squared, which is 0. Okay, and so notice that in this case I also got 0 for the second derivative. But if I look at this, this is going to be negative x to the fourth is just x to the fourth reflected across the x-axis. So notice in this case here we'll have a relative max. So in the second case, when we used the second derivative test and the second derivative turned out to be 0, we had a relative max. In one case we had a relative min, the other case we had a relative max. Let's take a look at one more function. H of x is equal to x to the third. If I'm looking for relative max or relative min, I'll first of all look for critical points, take the derivative, and the derivative is 3x squared. Setting that derivative equal to 0, because it's never going to be undefined, I get x is equal to 0. And so x is equal to 0 is a critical point. It's a stationary point because it makes the first derivative 0. If I look at the second derivative of h, trying to use the second derivative test, I'll get 6x squared. And if I evaluate that second derivative at 0, I get 6 times 0 squared, which is equal to 0. And notice in this case, if you remember what x to the third looks like, this function looks like this. And notice we have a critical point because there's a horizontal tangent at x is equal to 0, but there's neither. All right, so what happened here? All right, in one case where the second derivative turned out to be 0 when we were testing, we had a relative min. In another case, when the second derivative turned out to be 0, we got a relative max. In another case, we didn't get either one of them. And so the moral of the story is that if the second derivative is 0, anything can happen. You could get a relative min, you could get a relative max, or you might not get either one of those. All right, so try a different test. Well, what else can we try? Well, we can try what's called the first derivative test, and we'll do that in the next video.